You're going to need to know how to convert from binary to decimal and vice versa, but you're also going to need to know how to work with hexadecimal and convert from binary to hexadecimal and vice versa and to decimal and all these different counting systems. So I'm going to do a short lecture on how to make that easy for you. Okay, if you want to learn how to use hexadecimal, one of the difficulties is that we're so used to using the decimal counting system. We're so used to using a base 10 counting system that if we try to switch to binary or hexadecimal, it's difficult at first. So if you want to learn how to do it easily, the best way to do it is to go back to how you learned how to count when you were a kid. So up here I've got 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, and these are the place values for base 10 decimal system, right? 10 to the 0 is the ones place, 10 to the 1 is tens place, 10 to the 2 is the hundreds place, and 10 to the third power is the thousands place. So if I wanted to write a number like 184, I'd need 1 100, I'd need 8 tens, and I'd need 4 ones, and I'd have the number 184. Now, this is so ingrained and taught to us from such an early age that we don't even think about it, but it's actually important if we want to learn other counting systems. So for binary is actually pretty darn easy. We've got powers of 2. The place values. So here's 2 to the 0 is the 1's place, 2 to the 1 is the 2's place, 2 to the 2 is the 4's place, 2 to the 3 is the 8's place, and so on and so forth. And if we wanted to say, let's say, write a number like 11, I only have 4 place values here, so I'm just going to do the number 11, then I'd need 1, 8, I'd need zeros in the 4's place, and I'd need a 1 in the 2's place, and I'd need a 1 in the 1's place, and now I'd have the number 11 in binary, right? And that brings up another important distinction between decimal versus binary, and that is the fact that in a base 2 system, and I'm over here right now, you only have, the reason it's base 2 is you only have 2 characters or 2 numbers, 0 or 1. So I only put 0 or 1s in the place values here, right, to have my number. But in base 10, we have 10 different characters, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so base 2, 2 characters, 0 and 1. Base 10, 10 characters, 0 to 9. And so over here, you can see that I've plugged in those characters. All right, now, hexadecimal. Hexadecimal is base 16. Okay, so we have 16 characters. We have 0 to 9, and then we have A, B, C, D, E, and F. And A is a 10, B is an 11, and let's say F is a 15, right? So it goes from basically 0 to 15 with A, B, C, D, E, and F as 10, 11, 12, 13, 14, and 15. So those are your characters, or essentially your numbers for a base 16 system. But aside from that, it works just the same as a decimal or binary system. We have place values. So we have 16 to the 0 power is the 1's place, 16 to the 1 is the 16's place, 16 to the 2 is 16 times 16, or the 256 place, and 16 to the third power is 4096, right? 4096, 16 times 16 times 16. Now the key is in this type of conversions that you're going to see on your certification exams is to be able to switch between decimal, or convert between, let's say, decimal to hexadecimal. So let's talk about how we can do that easily and give you a few tricks on how to make that happen quickly. Okay, so for instance, I've written 184 here in decimal. If I want to write 184 in hexadecimal, I'm going to follow the same system. How many 4096s will I need? None. How many 256s will I need? None. But how many 16s will I need? Well, I'm going to need some 16s, right? Well, if I 11, let's see here, 11 times 16, right, is 6, 1, 6, 1, is 176. So I'm going to need 11 sixteens. But I don't write 11, I write B. So I'll put a B in here because a B stands for 11 in hexadecimal notation, right? So that's 176. Now, how many powers of 1 will I need? Well, to reach 184, I need 8 ones. So I'll put 8 here. So in hexadecimal, and you'd write this, you'd see this written like this, x B8 or 0x B8, or it'll be written maybe like B8H for hex. But a B8 essentially is 184 equals 184. I'm not sure if that's on camera or not. 184 in decimal is B8 in hexadecimal. Now, if I wanted to write that in binary, I need to have my place values go a little farther. So my place values in binary are, and I'll do this in black, 128, 64, 32, 16, 8, 4, 2, and 1. Those are the place values, with this being 2 to the 0 in the 1's place, and this being 2 to the 7th in the 128th place. So in binary, if I want to write 184, how many 128s will I need? Well, I'll only need 1. How many 64s? 0. How many 32s? 1. Now I have 128 plus 32 is 160, right? How many 16s? 1. There's 176. How many 8s? 1. That's 184. So this is going to be a 0, and this is going to be a 0, and this is going to be a 0. So 1 0 1 1 1 0 0 0 is 184 in binary. And so now we've written 184 in 3 different counting systems. Now, one thing that's going to be it's pretty useful is how to a trick for doing this quickly. So especially this is good for a larger number, but another trick that you can use is taking an 8 bits, and in computers everything happens, it seems like a lot of things happen, and not everything, but a lot of things happen in 8 bits at a time, or 1 byte at a time, right? Well, if we take these 8 bits right here, right, and we divide them into what's called 2 nibbles, right, and 2 nibbles would be 4 bits each. So we take these 8 bits and 1, 2, 3, 4, and we divide them in half, right, into 4 bits, right? We can treat each 4 bits separately. So instead of being the 128's place, the 64's place, the 32 16, treat each 4 bits, even though we have 8 bits total, just treat them as 4 bits each. So in other words, this would be the 8's place, the 4's place, the 2's place, and the 1's place. And this would be the 8's place, the 4's place, the 2's place, and the 1's place, right? And if we do that, right, we can then count each one separately. In other words, these 4 bits, right, 4 bits, well, let's count them up. An 8, a 2, and a 1 equals an 11, right? And an 11 in hexadecimal is a B. Okay? 11 in hexadecimal is a B. And if we take these 4 bits, an 8, 4, 2, 1, we've got an 8, we've got no 4, no 2, no 1, so this is 8, then we just write that as an 8. And now we've got our B8. So we could take, in binary 8 bits, divide them into chunks of 4 bits, and we can easily convert 4 bits to our hexadecimal character. Now, why is that? Well, 4 bits, okay, is 16 values. In other words, 2 to the 4th power equals 16, right? 2 times 2 times 2 times 2 is 16. So each character in a hexadecimal system is the equivalent of 4 bits, right? Because of the values 0 to 15, let's say. All right? So 8 plus 4 plus 2 plus 1 is 15, but if you had all zeros here, you'd have 0, so you have to count from 0 to 15 for a total of 16 values. Anyway, this is a neat trick, and it'll help you a lot on your certifications by taking 8 bits, dividing into chunks of 4 bits, and then easily converting to a hexadecimal number. And you can do that vice versa as well.